While solving electromagnetic problems, we require many types of mathematical tools. For example, differentiation, integration, vectors, maximas, minimas, etc. etc. But my dear, all of these tools, I think integration might be playing very important role in our electromagnetics after the vectors. The formal definition of integration is area under the curve. But when we consider an electromagnetics, which actually deals with vectors, vector fields and their complex functions, the interpretation of the integration into the electromagnetics is quite interesting, as we are going to see. But before moving ahead, let me make a difference between a vector and a vector field. The formal vector you already might be knowing. A vector is the one which is having magnitude as well as direction. For example, let us say like this: 3ax plus 4ay plus 5az. X component is 3, y component is 4 and z component is 5. The pictorial representation will look like this. It is a line amongst 2 points having magnitude as well as direction. Now my dear, just think for a second. What would be the pictorial representation will look like if these x, y and z components are not constants, but these are functions of x, y and z? Can you imagine how the diagram could look like? It is very difficult to show pictorially, but I am giving you the basic idea. When the components of the vector are functions and they are not constants, they are functions, then rather than getting only one vector, we get a set of vectors, a bunch of vectors in the space satisfying certain conditions of the function. So instead of getting only one vector between 2 points, when the components are the function, then we get the set of vectors, the bunch of vectors, and such thing, my dear, such thing is called as vector field. So vector field is very easy to recognize. In any vector, if components are the functions of x, y and z, functions of rho, phi, z, r, theta, phi, whatever, which coordinate system do you use, whatever. But if components of the vector are functions, then such vector is called as a vector field, and it is a more generalized term. Rather than getting only single line, single vector between 2 points, in such case we get set of vectors into the space, and such set of vectors satisfying certain function we generally interpret as a vector field. My dear, this concept of vector field is going to be used again and again in our electromagnetics. Actually, we are dealing with only fields in the electromagnetics: electric field, magnetic field, etc. Consider any vector field, just like electric field is present in the region, and consider that any vector or line AB is present in this field as shown on your screen. And assume that we want the product of this length or vector AB and component of the field along this line at every point. Once again I am repeating, let us assume that we want to find out the product of length AB or vector AB and component of the field E along this line AB at every point. So our required product will be written as E dot AB. My dear, we have used the dot product. You already might be knowing about the vector products. We have two types of vector products: cross product and dot product. We use a dot product when we want the product of a given vector and component of the other vector along the given vector AB cos of theta. In such case, we will use the dot product. Just remember the formula for work. Work is defined as force into displacement along the force. That means component of the displacement along the force. So we write the formula for work as F dot X. Likewise, in our case, we want the product of the line or vector or length AB and component of the vector field along this line at every point of the line, and hence we will use the dot product as we have just used. Now, my dear, as we have just discussed, any vector field is going to be the function of x, y and z, function of rho theta phi, r theta phi, whatever. It is going to be the function. And when we deal with the function, we have to use the integral calculus. We cannot find the product manually. We have to use the mathematical tool, that is integral calculus. And remember what we do in the integral calculus. In integral calculus, first of all, we find the value of the product. We find the infinitesimal value of the product by considering the small or infinitesimal element, just as you have solved in your mathematics, dx, dy, dz, like this. So in integral calculus, first of all, we find the infinitesimal or small value considering the infinitesimal differential element. Then in second step, we integrate that small value, we integrate that infinitesimal value over the complete range to get the final answer. In our case also, we will do same thing. We want the product E dot AB or E dot complete length, but first of all, we find the small or infinitesimal value of the product by considering the very small length present over AB. Let us say dl vector. So our infinitesimal or small product will be E dot dl vector. This dl vector or dl will be our differential element, very small length, infinitesimal length, or you can say differential element of the integral. So our small infinitesimal product is E dot dl. Now my dear, to get the final answer, we have to integrate this infinitesimal value over the complete range of the line. In our case, over the complete length of the vector. So you have to put proper limits, lower limit and upper limit from A to B. So the final answer, the final product will be written as shown on your screen. Integration from A to B or line integration E dot dl. And my dear, this is called as the line integration in our electromagnetics. So what I am trying to convey you, line integration in electromagnetics in very sophisticated way can be remembered as it is the product of the vector or the line and component of the field along this line present at every point of the line. Now my dear, let us try to understand this differential length dl or dl vector in more detail. And for that, first of all, let us recall how do we generally integrate in the mathematics. Most of this time in mathematics we solve this integration f of x dx. My dear, for understanding purpose, by analogy we can say that this dx is the infinitesimal length or differential length along the line parallel to x-axis. That means we are integrating this f of x along the x-axis, and dx is small length over that line, small infinitesimal length. Now in electromagnetics we deal with 3D space. So you know, our differential length in electromagnetics cannot only have dx or only dy or only dz, but rather it should have all these differentials as you can see on the screen. So it is defined as dx dy plus dz az. My dear, you can notice also one thing, we represent this differential length in vector form because the reason is quite obvious, as I just explained. We deal with vector fields in electromagnetics, so it is obvious that differential length should also be in the vector form. Dx or x component, we can say that dx is the differential length or infinitesimal length along x-axis, or more sophisticatedly, change along x-axis. dy, change along y-axis, differential length along y-axis. Similarly, dz, it is change along z-axis. So finally, the differential length dl vector is represented as dx, change along x, ax, plus dy, change along y, ay, plus dz, change along z, az.